Hello everyone. Today, we are tackling the 2017 VCE Physics Magnetic Forces question, a section where many students lose marks for the same reasons. We'll break down magnetic monopoles, DC motor forces, and the examiner reported mistakes so you never repeat them again. A group of students is considering how to create a magnetic monopole. Which one of the following is correct? A. Break a bar magnet in half. When you break a bar magnet in half, you do not isolate the north and south poles. Instead, individual magnetic domains realign at the fracture point, creating two smaller, complete bar magnets, each with its own north and south pole. B. Pass a current through a long solenoid. Passing a direct current through a solenoid generates a uniform magnetic field inside the coil and a diverging field outside, mimicking a traditional bar magnet. One end acts as a north pole where field lines exit, and the other acts as a south pole where field lines enter, maintaining a dipole structure. C. Pass a current through a circular loop of wire. A single current-carrying loop creates a magnetic dipole field. According to the right-hand grip rule, one side of the loop face acts as a north pole and the opposite face acts as a south pole. D. It is not known how to create a magnetic monopole. In classical electrodynamics, governed by Maxwell's equations, the net magnetic flux through any closed surface is always zero. This fundamental law states that isolated magnetic charges, monopoles, do not exist in standard macroscopic observations. While certain theoretical frameworks, like grand unified theories, predict their existence at extremely high energy scales. And quasiparticles resembling monopoles have been observed in condensed matter systems, like spin ices. It remains experimentally unknown how to isolate or create a fundamental magnetic monopole particle. Correct answer. D. It is not known how to create a magnetic monopole. The examiner's statistical data confirms this, showing that 65% of students correctly selected D. Figure 2 shows a schematic diagram of a simple DC motor. It consists of two magnets, a single 9.0 V DC power supply, a split ring commutator, and a rectangular coil of wire consisting of 10 loops. The total resistance of the coil of wire is 6.0 ohms. The length of the side JK is 12 centimeters, and the length of the side KL is 6.0 centimeters. The strength of the uniform magnetic field is 0.50 T. Calculating the magnitude of the force. To find the size of the magnetic force acting on side JK, we follow a two-step calculation process. Step 1. Calculate the current, I. Using Ohm's law, determine the current flowing through the rectangular coil. Current equals voltage over resistance. Step 2. Calculate the total magnetic force, F. Because the coil consists of multiple loops, the magnetic force formula for a current-carrying conductor is scaled by the number of turns, N. Force equals the loop of coil, strength of magnetic fields, current and length of wire. Determining the direction of the force. To find the exact directional vector from the choice compass, at F, we apply right-hand palm rule, or Fleming's left-hand rule, to the side JK. Current, I flows from the positive terminal to the negative terminal. Following the commutator connection, current travels from J to K, into the page, away from the viewer along axis B. Magnetic field, B points from the north pole to the south pole, which is from left to right, towards direction C. Force, F pointing your right-hand fingers to the right, C, and your thumb into the page, B, positions your palm facing straight down. The vector pointing straight down corresponds to label D. Direction, D down. According to the statistics, the average score for this 3-mark question was 2.1 out of 3, with 48% of students achieving full marks. The examiner noted that the most frequent errors leading to mark deductions included omitting the multi-turn factor, forgetting to multiply the final force value by the 10 loops of wire, N equals 10. Unit conversion errors, failing to convert the length of side JK from centimeters, 12 centimeters, into standard SI metric units, 0.12 m. Misapplication of hand rules, incorrectly orienting the current or field vectors, leading to an incorrect directional letter. What is the size of the force acting on the side KL in the orientation shown in Figure 2? Explain your answer. 2 marks. Suggested exam response. Size of the force, 0 n, or 0, 1 mark. Explanation. The current flowing through side KL is running parallel, or anti-parallel O in the same direction, to the external magnetic field lines. Therefore, no magnetic force is experienced by this segment of the coil. 1 mark. The question achieved an average score of 1.5 out of 2, with 69% of the cohort gaining full marks. Critical wording pitfall. The chief examiner explicitly noted a common conceptual error in student phrasing, stating that the force is 0 because the current is not perpendicular to the field. A force does exist at oblique angles, 30 degrees, 45 degrees. It does not require a perfect 90 degrees angle to experience a push. The force only drops to 0 when the wire is strictly parallel, theta equals 0 degrees, or anti-parallel, theta equals 180 degrees, to the magnetic flux lines. Loose phrasing like "it isn't at a right angle" will lose the explanation mark. Final summary: magnetic forces and DC motor concepts. This presentation reviewed key ideas from the 2017 VCE Physics examination on magnetic forces and DC motor operation. Magnetic monopoles. Breaking a bar magnet does not produce monopoles, each fragment retains both poles. Physics has not yet discovered a method to create true magnetic monopoles. DC motor analysis. Using a 9V supply, 10-turn coil, 0.50 T field, and known dimensions, the current in the coil is 1.5 A. Side JK experiences a magnetic force of 0.90 N, directed downward. Side KL experiences 0 force because its current is parallel or anti-parallel to the magnetic field. Examiner insights. Common errors include forgetting the number of turns, incorrect unit conversion, and misusing hand rules. Magnetic force only becomes 0 when the conductor is exactly parallel, 0 degrees, or 180 degrees, to the magnetic field, not merely not perpendicular. Key takeaways. Apply equals and multiply by the number of loops. Use the correct hand rule to determine force direction. A conductor in a magnetic field experiences force except when perfectly aligned with the field lines. At the end of every lesson, I want to leave you with one idea: learning becomes powerful when you climb the logic ladder. Physics moves from situations to models to equations. Chemistry builds from structure to property to reaction. Biology grows from variation to adaptation to survival. Different subjects, but the same underlying logic. When you learn to decode systems, build ladders, and construct logic, you don't just solve problems, you understand how they fit together. If you'd like to keep climbing this ladder with me, You can find more lessons, breakdowns, and reconstructions on my channel. Thanks for learning with me today.